There we go. So as always, I'm making sure to record our meeting tonight. So if you ever want to go back and watch the recording, watch the notes that we went through here this evening, it'll be posted right here in the class recording section of the Google Classroom before the end of the day today, usually within a few minutes of finishing up class. I try to get that taken care of right away. So if we scroll down a little bit forward, we can see that we are now in week 5 of term 3. So we've got week 5, 6, 7, and 8 to go. So we have officially passed the halfway mark for this first term of the spring. So we're 4 weeks down and 4 weeks to go. So in week 5, we're going to be talking about chemical reactions and chemical equations. So we're going to be looking at all the different ways that atoms and compounds combine and rearrange with each other to make all of the sorts of different materials that we see in the world around us. All right. So obviously we didn't have any class or assignments on Monday, so we'll jump right here into the notes for Tuesday. So today we're going to be talking about chemical reactions, the kind of bigger picture look at what's happening when we're forming all of these new covalent and ionic bonds with these different atoms and compounds that we are dealing with. So hopefully some of the stuff that we talk about today might actually sound a little bit familiar to you. And that's because we've partially kind of already talked about chemical reactions when we were talking about chemical changes. So remember earlier in the term, we talked about physical properties and chemical properties and physical changes and chemical changes. Well, chemical reactions is kind of the more scientific or the more specific way of talking about chemical changes. So just like when we were talking about a chemical change from a couple weeks ago, chemical reactions are all about when we have one set of substances and it goes through this chemical change to form a new set of substances. So the chemical change is kind of just describing what is being changed or how it's changing. The chemical reaction is the whole process of looking at the starting material, looking at how it's changing, and then seeing what we have as our ending material. So there are a whole bunch of different chemical reactions that are happening around you every day that you might not even realize. So things like growing, right? This little caterpillar right here is eating the parts of this leaf. It already took a little chunk out of here. And so it's eating away, and it's taking all of that plant material that it's eating, breaking it down in its stomach and turning that into energy and new caterpillar cells for growing. Eventually, it'll change those caterpillar cells into butterfly cells. But all of that happens due to chemical reactions. We start off with leaf and plant material, and we end up with new substances like energy for the caterpillar or new caterpillar cells or the material that we need to make a butterfly. So we're taking one set of substances and turning it into something new. Ripening is another everyday chemical change that I'm sure a lot of us are all too familiar with, right? You buy something at the store. Sometimes it starts out as not very ripe and you have to let it sit for a couple days to get to the correct ripeness. Things that come to mind like that for me are like peaches and avocados and stuff like that. Or you have things like bananas or tomatoes where generally you buy them ripe, ready to go. And then if you don't eat them soon enough, they'll start to become overripe and really gross and nasty, and you don't really want to eat them, right? So the ripening that's happening is a chemical reaction. We're taking the original particles that were in that fruit, say. So a lot of times in fruit, ripening happens because we take big starch molecules, like think about a banana, right? Or like a tomato, like this guy here. A green banana or a green tomato is really starchy. It's kind of crunchy. It's very firm. And then as it ripens, as the banana becomes yellow or as the tomato becomes red, it starts to soften up. It becomes a little bit sweeter, usually. And that's because those big kind of starchy structural sugars are being turned into smaller, easier to digest sugars. So we're starting off with one set of materials, but we're turning it into something different, something new. So we have a chemical reaction. Decomposing, so if you let something sit out for way too long, especially things like bread, right? If you look at really old bread, it starts to get nasty because there's all this mold and fungus and bacteria and stuff that are growing on it. Well, all of that mold and fungus and bacteria are taking the bread, in this case, like a bagel, they're taking it and breaking it down into food that they can use. So they're breaking it down for their own energy. They're taking that bread substance and turning it into a substance for their energy. So chemical reactions occurring, changing a substance from one thing to another. Another big one that we talked about with the chemical change was things like burning or combustion. So by heating up something in the presence of oxygen, some things have a tendency to catch on fire when you do that. And when they do, the reason why the fire is hot and you see the light coming off of the flames is because of the chemical reactions going on in the fire. In this case, we're taking wood and turning it into smoke and ash. So the smoke coming up out of the fire is obviously a different substance than the wood that we started off with. Those are two different chemicals, two different sets of substances. So we must have had a chemical reaction in order to get that to happen. So all about change, all about forming new substances from our old substances. So there are a handful of different ways that you can tell that a chemical reaction is happening. So one of the signs of a chemical reaction is bubbles appearing in your substance. Now, this does not count when we're talking about like boiling or vaporizing something, right? Because in that case, we're turning liquid water into gas, water vapor. So that's not really a chemical reaction. It's doing that because we heated it up really hot. However, if we mix two different chemicals together and then all of a sudden they start bubbling and fizzing up, that means that you have some sort of chemical reaction going on. So, for example, when you like drop an Alka-Seltzer tablet into a glass of water, or when you mix baking soda and vinegar and it creates that big kind of cartoon foam spray that you see in like the shows when they make like the volcano for the science fair. All that bubbling is happening due to chemical reactions between the two substances that you're mixing. So the reason why the Alka-Seltzer tablet fizzes and bubbles when you drop it into water is because the Alka-Seltzer and the water are going through a chemical reaction to produce a new substance, which is a gas. So that gas is forming little bubbles and coming up out of the water. Another sign that a chemical reaction could be happening is kind of like the opposite of this. It's instead of forming bubbles, instead we form a solid. So in science, we call that solid that forms due to a chemical reaction. It gets a fancy word called a precipitate. So this happens a lot in scientific experiments and like organic chemistry type of experiments, where you mix two different liquids, two different substances together, and then all of a sudden a new solid appears in your beaker or in your test tube. So it wasn't there before, but now due to the chemical reaction, it has appeared. A color change happening can be a sign that a chemical reaction is going on. Now, this does not mean that you take the purple Kool-Aid mix and you dump it into the clear water and now the water is purple. That's not really the color change that we're talking about. Instead, this would be like if you combine two different clear liquids and all of a sudden they turn green in your beaker. Or like we were talking about earlier with the fruit, a banana starts out as kind of this bright green color, and then as it ripens, it changes to yellow and eventually brown and mushy and gross. So that color change from green to yellow to brown is due to the chemical reaction, due to the ripening of the banana. So that's the kind of color change that we are talking about. You can also get temperature changes with chemical reactions, and we're also going to talk a lot about this a little bit later on. So some chemical reactions give off heat, the temperature gets hotter, things like burning, like we were talking about earlier. Or sometimes a chemical reaction can absorb heat, make things cooler as the chemical reaction goes on. Light can also be given off during a chemical reaction. So with the burning that we talked about, right, when you set something on fire, that produces a lot of light because the burning of the fire releases those flames, and the light is part of the chemical reaction. So the light from the flames is a sign that a chemical reaction is happening between the heat and the wood and the oxygen around it. Also, some animals can produce light due to a chemical reaction. Things like fireflies or this jellyfish down here, they have special proteins in their cells. And when they break down these proteins, light is given off as part of that breakdown reaction. And so these animals are able to produce their own light due to chemical reactions happening in special areas of their bodies. And then finally, some chemical reactions, obviously there's a lot of chemical reactions that you probably should not taste or smell too close, but some of them, especially the ones involved in food, do result in a change of smell or taste. So again, going back to like the tomato example from earlier, the banana example, a very underripe tomato tastes different than a ripe tomato, which tastes different than an overripe and kind of gross, mushy tomato. That's because the chemicals that are changing inside of that tomato, when you eat them, your tongue comes into contact with them, and so they taste different depending on what type of chemical that they are. If you're eating a fairly green banana, right, you get kind of that starchy taste in there. And then a yellow banana is a little bit sweeter and a little bit squishier. And then like a really brown banana is going to be kind of like sticky sweet, like overly sweet, extra mushy. And that's all due to the chemical reactions happening inside of the banana or tomato or whatever fruit or food that it is that you're ripening. So again, all these things are happening because we're making new chemicals. So either we're getting some new bubbles to appear, or in animals like fireflies and jellyfish, we call the light that comes off bioluminescence, basically just a fancy way of saying light from a living organism. So these, or colors changing, or a new solid being formed, all of this is due to these different chemicals that we're producing. Because again, in a chemical reaction, we're creating new substances. We're creating things that were not there before. So sometimes when that happens, we can get one or more of these signs to appear. One or more things that tell us, hey, something is going on with these chemicals. We're getting something new, something different, something that was not here before. All right. Does anybody have any questions about chemical changes or chemical reactions so far?
No.
Joseph.
No questions.
Cool. So like I said, a little bit of stuff that we've kind of heard about before with those chemical changes. A little bit of kind of new stuff here. So one of the other new things that I wanted to talk to you about was the specific vocabulary, the specific wording that we have regarding chemical reactions. So like I said, it's all about taking one set of things and turning them into something new, something different. So scientists have specific words for our starting material and our ending material. So the starting material in a chemical reaction are called the reactants. These are the substances that react. They're going to be reacting together in order to create our new materials, our new products. So our starting materials, the things that we are starting with that are reacting together, we call them the reactants. The ending materials, the stuff that is new, the stuff we end up with, are called the products. So they're called the products because they are produced by the reaction. So we start with the reactants. They react together. They are combining together in different ways. They're creating maybe some bubbles. They're creating some heat. And we're ending up, or the reactants yield or produce the products.
No miro. Súbilo.
All right. Araceli, you have a question?
Tiene que ser 3 palabras para que...
Oh, okay. Back to me. All right. All right, so we start with our reactants, and then the chemical reaction happens, and we make our products. So the arrow here, a lot of times when you see a chemical reaction written out, it'll look kind of like a math problem, only instead of an equal sign, it'll be an arrow, like this one. And so the arrow just means that the reactants yield, or the reactants produce the products. So our reactants are our starting material, and our products are our ending material. So one very, very common or very, very famous chemical reaction that happens all around you in the world every day is called photosynthesis. Now, before I tell you guys what exactly photosynthesis is, does anybody have kind of a general idea or a general explanation for photosynthesis? What does that mean?
The way that plants grow?
Exactly. So photosynthesis is used by plants, and it's used by plants to make their own food. So obviously, plants are not like us. They don't have to eat other plants or other animals to survive, for the most part. They make their own food by sitting in the sun. And the photosynthesis equation describes how plants make their own food. So it's a big, somewhat complicated equation, but I'll walk you through it piece by piece. So over here on the reactant side, we have CO2, which is carbon dioxide, and H2O, which is water. So carbon dioxide and water are our reactants, our starting material over here on the left. When the plant gets energy from the sunlight, it can turn this carbon dioxide and water into glucose, which is this big 6-carbon molecule right here, which is a form of sugar that they use for food, and oxygen. So we, as humans, breathe out the carbon dioxide that plants need, and then through photosynthesis, plants make the oxygen that we need to breathe. So our reactants are CO2 and H2O, also known as carbon dioxide and water. And our products are C6H12O6 and O2, also known as the sugar called glucose and oxygen. That's stuff that we breathe in. So this is a classic chemical reaction, right? We have some starting material, and then we turn them into something different, something new, something that was not there before, right? Glucose and oxygen are obviously not the same chemicals as water and carbon dioxide. They are different chemicals, different combinations of atoms. So our products are different from our reactants, which is what tells us that a chemical reaction has occurred. Plants take in carbon dioxide and water into their leaves, and they use the energy from the sun to turn that carbon dioxide and water into sugar that they use for energy, and oxygen, which they then release from their leaves as kind of a byproduct, as like an extra thing that they don't really need, but it comes along with the equation. So starting off with one set of chemicals and ending with something new, something different. One thing, though, that I want to point out is that one important aspect of chemical reactions is that we cannot add or destroy any new or different atoms into this equation. We can only rearrange them. So what do I mean by this? What do you mean I can't add or destroy? So if you look over here on the reactant side of our equation, we have some carbons and our carbon dioxide. We have some oxygens over there too. And we also have some hydrogens and some oxygens. So our different atoms on the reactant side, we have some C's, we have some O's right here and here, and we have some H's. So C's, O's, and H's are the only atoms, the only different atoms that we have on our reactant side. What about our product side? What are the different atoms that we have over here in the products?
Would it be oxygen and glucose?
Close. So those are the overall things that we have produced. Those are the two kind of elements or compounds. What about like the different atoms? So like what different letters do we have on the product side? Oh, and Helga has nailed it. We have C, H, and O in the products. All right, so there's some C's right here. There's some H's right here, and some O's right here and right here. So on the reactant side, we have C's, O's, and H's. And on the product side, we have C's, we have O's, and we have H's. So what I mean by when I say we can't add or destroy any atoms, only rearrange, is that we don't have any new or different atoms on the product side. Instead, we have rearranged them in a different way than they were before. So we have C's, O's, and H's on the reactant side, which means that we can only have C's, O's, and H's on the product side. We can't have any like N's or any F's that come in and get added. And we also can't get rid of any of them, right? We have O's over here, so we have to have O's over here as well. We have H's over here, so we have to have H's over here as well. We can't lose any of the atoms that we started with. So instead, what do? We can only rearrange them. So we added some H's to the C and O over here and kind of changed around how many of them they were. And we took away these H's from over here. So now we only have O's. All the same types of atoms, but we rearranged them in a slightly different configuration. So it's kind of like we took these guys apart into pieces and rearranged how they were added together. We didn't add in any different pieces, and we didn't take away any of the pieces. We just rearranged them. So that is a really critical part of chemical reactions, a really important thing to take away from our notes about chemical reactions today, is that we can't add or destroy any atoms. We can only rearrange the ones that we start with. So whichever atoms that we have in the reactants, we have to have those same atoms in the products. There can be different numbers of them. They can be bonded together in different ways, but we have to have the same types of atoms. So again, we had O's and H's and C's in the reactants, which means that we have to have O's and H's and C's in the products. No more different atoms and no fewer atoms. Only rearranging the ones that we start off with. All right, I know that's kind of a lot. That's one of the trickier parts of chemical reactions that we're going to talk about today. So does anybody have any questions about the photosynthesis equation, the reactants and the products, or what it means about rearranging the atoms?
No question.
All right, great. Good to know. All right, so we have our reactants. They're turning into some different products than we had before, but we're rearranging the atoms that we start off with. So they're different overall products, but they are made out of the same atoms that we started with. The same thing is true of energy. So it takes energy for reactions to happen. Either they give off energy or they take in some energy. And so it's the same general concept, is the energy might be transformed into different forms. It could be electrical energy, it could be heat energy, it could be light energy, it could be chemical energy. There's all sorts of different forms that the energy in a reaction can take, but you have to have the same total amount of energy at the beginning of the reaction versus at the end of the reaction. So like in this little example here, for a light bulb, we put in 100 units of electrical energy. So we have 100 electricity coming in through the wall and through the cable. And then 5 of those will be transformed into light energy and be given off as light that we can see. And this is like one of the old school light bulbs from like the 80s or 90s. So 95 of that is going to go into heat. So like if you've ever been around old light bulbs that get really hot, if you've had them on for like 20 or 30 minutes, that's because they give off a lot of heat as part of being turned on. So it's still 100 total, right? 5 and 95 together makes it 100. It just got transformed into different ways. Kind of like we have the same total different types of atoms in our products versus our reactants. They just get transformed in different ways. They get rearranged and put into new compounds, new equations. So specifically in that photosynthesis example that we were looking at earlier, the energy from the sun that the plants are getting is coming in as light energy. So the reason that plants are able to do photosynthesis is that they're absorbing light energy from the sun. When they turn that into glucose, that is it being stored as chemical energy. So sugar is what a lot of plants and a lot of animals as well use for chemical energy. So light energy got transformed into chemical energy. And then when you eat that food and use the energy from it to move around and go do activities and stuff, then it gets transformed again into something like mechanical energy or energy of motion. So the energy is being transformed through the different chemical reactions and is being used in different ways. But again, however much energy you have at the start of a reaction, you have to have that much be produced throughout the reaction. So when we're looking at chemical reactions and sort of the energy that they are dealing with, there are two kind of really broad categories of chemical reactions we can have. We can have reactions that release energy, and we can have reactions that absorb energy. So the first one that we're going to talk about that releases energy is called an exothermic reaction. So in an exothermic reaction, over the course of the chemical reaction, energy is being released into the environment, a lot of times as heat. So the energy going into the surrounding area gets turned into heat energy, which then, if you remember back to when we talked about like our solids and liquids and gases, that heat causes those little atoms, those little particles, to start moving even more. And that's what we read as temperature. So exothermic. Exo is, I think it's like Latin for going out or being released. And then thermic is like thermal, like heat. So digesting food is a great example of exothermic reactions. Our body consumes a lot of food. We need a lot of energy to keep up our body's activities. One of the reasons for that is because of our high internal body heat. I'm guessing that by now, in these COVID times, everybody has had their temperature checked at least once, either going to the doctor or going to like even a store. Sometimes they'll check your temperature at the door. If you ever come back to the Excel Center because you're dropping something off or coming into a class, we'll check your temperature before you come in. And a normal human body temperature is around 98.6 degrees Fahrenheit. Obviously, 98.6 is pretty hot, especially when it's, I don't know, 50, 60 degrees outside. So when we digest food, a lot of that energy from our food is turned into heat in our bodies. We're breaking down those big food structures, and some of the energy being released is heat that we use to keep our internal body temperature nice and toasty. Decomposition is a very similar thing, only instead of eating food, eating other living plants or animals, it's things that are breaking down like dead and decaying plants and animals, but still converting that biological matter into energy for things like bacteria and mold and stuff like that. Obviously, burning fuel, whether that's wood or propane or gasoline, are very exothermic reactions, right? They're giving off a lot of heat and sometimes light as well. So not all exothermic reactions give off light. Obviously, down in your stomach, when you're breaking down food, it's not creating like, there's not like a light show going on in your intestines. But things like burning and combustions do create light. So they create flames that then we can see as light being produced as part of this chemical reaction. Another famous exothermic reaction that we don't really get down here in Texas because it doesn't get that cold enough. But when I lived in Ohio, sometimes when it was like 15, 20 degrees outside, inside of my gloves, I put these little hand warmer packets. If you ever seen them, they kind of look like those silica gel packets that you get in like a new pair of shoes. And they're these little packets that when you squish them together, so you kind of crumple them up and then put them inside of your glove or inside of your boots. When you crumple them up, that brings two different chemicals into contact with each other. And those chemicals do a slow exothermic reaction with each other. So the reaction that they do is obviously safe to have near you and it's non-toxic, but it produces a lot of heat. So it's a nice way to keep your hands and feet warm when it is super duper cold and chilly outside. So exothermic means heat is being released, is being given off into the environment. The flip side of that is if we're absorbing energy, we're taking in energy in order to, usually to build stuff. So that is called an endothermic reaction, where energy is being absorbed from the environment. So exothermic, heat going out. Endothermic is heat going in. So endo is like in, kind of like the beginning right here. So energy is being absorbed from the environment into the reaction. A lot of times this is happening when we're forming new chemical bonds, new structures. So a lot of that chemical bonding that we were looking at the other day with the covalent bonds and the ionic bonds, in general, there is a little bit of energy that's required in order to do that. And so if you're building a big structure with lots of bonds in it, then you're going to need a good amount of energy from the environment. Maybe it could be light energy in the case of photosynthesis right here, or it could be heat energy that's being absorbed in order to help the reaction go on. So photosynthesis is a great example of these endothermic reactions. Again, we have the light that's being absorbed by the leaf, and that's helping take those little carbon dioxide and water molecules and turn them into that big glucose molecule. So glucose is a big molecule. It has lots of atoms in it. And so it takes some energy in order to form that glucose molecule. The plant uses energy from the sunlight in order to turn carbon dioxide and water into glucose. Now, with exothermic reactions, there's almost always some sort of heat that's being given off to the environment. And endothermic reactions, there's not necessarily always going to be like a drop in temperature, even though they're the opposite of exothermic reactions in structure. That doesn't mean that they're always going to make things get colder. There are some endothermic reactions that do cool things off, but it's not as common as kind of releasing energy into the environment. But endothermic reaction is absorbing energy, usually to build some sort of large number of chemical bonds for a big molecule like something like glucose, a big sugar molecule like that guy. So whether you're absorbing light from the sun or heat from a heat source nearby, you're using that energy in order to build, in order to create these bigger molecules. Whereas a lot of times in exothermic reactions, it's big molecules that are being broken down into smaller ones, and then energy or heat is kind of being given off as a result of that breakdown. All right. So anybody have any questions about exothermic or endothermic reactions?
No questions here.
All right. Cool, cool, cool. So I believe that actually brings us to the end of our chemical, oh, there you go. Photosynthesis, very classic endothermic reaction. So main takeaways about our chemical reactions from today. They're what occur when we're changing from one set of substances to another. There are all sorts of signs that a chemical reaction could be going on, from gases or solids appearing, colors changing, tastes changing, light and heat being given off. All these can tell you that a chemical reaction is going on with your substances. We start off with our reactants. They react together and combine their atoms in different ways to form our products. But the reactants and the products are still made out of the same general types of atoms. With photosynthesis, we have CHO on the reactant side and CHO on the product side. So we can't get rid of these atoms. We have to just rearrange how they're attached to each other. So our reactions can be exothermic, where they release energy out into the environment, or they can be endothermic, where they absorb energy and use that usually to build up some sort of structure that has a lot of chemical bonds. So for the daily assignments for today and tomorrow, they should be hopefully pretty straightforward. For today's assignment, I just want you to give me a simple list of the different signs that a chemical reaction is occurring. So what are some of those different ways that tell you that some new substance is being produced, that some sort of chemical reaction is going on? And then for the assignment that'll go up tomorrow, it has to do with exothermic and endothermic reactions. So basically, I just want you to kind of contrast the different types of reactions. Tell me a little bit of what makes a reaction exothermic versus what makes a reaction endothermic. Again, a couple quick and easy assignments to kind of recover from the midterm that we just did last week. I know earlier I was saying that I didn't get the notes for today posted until just before class started. So if you tried to do the Tuesday assignment, but now realize that maybe you got it a little bit wrong and want to go back and fix it, you are more than welcome to. I won't start looking at submissions for this one probably until Thursday or Friday this week. So if you did the chemical reaction steps already, then, but you want to go back and change some of your answers, you are more than welcome to go do so. All right. Anybody have any final questions about chemical reactions or the Tuesday or Wednesday assignments?
No questions.
No question.
All righty.